The bell casting process begins with the construction of a precise mold, which requires three main components: the core, the false bell, and the mantle. The core is built from bricks and clay, shaped using a rotating template mounted on a spindle. It represents the inner cavity of the final bell. Next, the false bell is formed over the core using sandy clay and graphite, which allows it to be later removed easily. This false bell is shaped exactly like the final bell and serves to create the cavity between the core and the mantle. After forming the false bell, wax decorations are applied. These include inscriptions and a wax portrait of Patriarch Daniel, created from a plaster mold. Hot wax is poured and sculpted onto the surface of the false bell to ensure a smooth and detailed finish. The decorations are carefully aligned and bonded using modern tools like glue sticks, although the coarse sculpting and shaping techniques remain largely traditional. Once the waxwork is complete, a fine decorative clay layer, mixed using traditional recipes, including ingredients like beer, is applied over the wax. After drying, additional thicker clay layers, mixed with hay and horse manure, form the rigid outer mantle. This layer is reinforced with steel rings and filled with furon sand, a modern hardening material, to ensure structural stability. Ceramic tubes are embedded to guide the molten metal during casting. The false bell is then removed by disassembling the mold. This step reveals the final mold cavity between the core and the mantle. All wax is burned out or removed with gas torches, leaving behind detailed impressions in the mold. The entire assembly is thoroughly dried and preheated. The bronze alloy, heated to 1,100 degrees Celsius, is poured into a large casting pit through a specially built masonry funnel. The metal flows downward and then rises from the bottom through the ceramic channels, ensuring a dense, high-quality casting. The bell is then left to cool for several days. Once solidified, the mold is broken apart and the bell is revealed. This monumental bell stands 3.13 meters high, 3.36 meters wide, and weighs over 25 tons, with walls up to 27 centimeters thick. Over 4,000 working hours went into its creation, marking it as the largest free-swinging church bell in the world. Wax patterns are created and assembled into trees, then coated multiple times with ceramic slurry and refractory sand to form a mold. After drying, the wax is melted out and the molds are fired at 1,000 degrees Celsius. Molten aluminium is then carefully poured into the preheated ceramic molds for casting. The anodizing process begins with rinsing, followed by alkaline etching to remove surface irregularities. After another rinse, deoxidizing eliminates natural oxides to prepare the aluminum surface. Anodizing is then performed in a sulfuric acid bath at 18 to 22 degrees Celsius, forming a durable porous oxide layer. A rinse removes residues before sealing the pores in 95 degrees Celsius deionized water. Drying completes the process. Final inspection checks coating thickness, surface finish, and color uniformity for quality assurance. Waldrich-Siegen specializes in dimensional accuracy, heavy-duty machine tools engineered for the complete machining of large-scale components across diverse industrial sectors. The Profi-Mill portal milling machines, available in table, twin table, and gantry configurations, are designed for the high-efficiency machining of oversized, complex geometries. These machines incorporate fully hydrostatic guides on all linear axes, ensuring zero backlash, high damping, and long-term geometric stability. The gantry version, with its space-saving footprint, is employed for heavy-duty operations such as the roughing and finishing of diesel engine blocks or machine beds. An integrated automatic tool changer facilitates rapid tool exchanges, reducing idle time and increasing machining throughput. The Profiturn H horizontal lathes are engineered for the precision turning of rotationally symmetric workpieces, with diameters up to 7 meters and lengths up to 30 meters. Equipped with hydrostatic main spindles and optional integrated milling units, these machines are capable of pure turning, turn milling, and crankshaft machining. The process typically begins with the workpiece mounted between centers or on steady rests, followed by rough turning, fine turning, and milling cycles executed without repositioning to ensure concentricity and geometrical fidelity. The Profiturn 5 vertical lathe features a cast-iron rotary table and a hydrostatically guided ram, optimized for large-diameter workpieces. Automated tool and machining unit changers enable multifunctional operations. During machining, the workpiece is rotated by the torque-heavy table while the vertically oriented tool head performs precision cutting. The hydrostatic system ensures minimal wear, high positioning accuracy, and dynamic rigidity under load. The Profiturn M Mill Turning Center provides complete 5-axis machining capabilities for complex parts, such as turbine rotors and forged shafts. With a modular box-in-box architecture and high-torque masterhead interface, the machine allows sequential turning, milling, boring, and grinding, conducted on a single setup for maximum dimensional accuracy and minimized cycle time. Lastly, the Profit Grind roll grinders are designed for ultra-precise grinding of heavy rolls. Hydrodynamic steady rests, micron-level concentricity control, and high spindle power enable consistent surface quality and dimensional repeatability, even on rolls weighing up to 300 tons. The production of copper cookware at Raffoni starts with selecting high-quality copper sheets, typically 2.5 millimeters thick. These sheets are precisely cut into the required shapes for various cookware items. The copper is then heated in a furnace to soften it, followed by manual hammering to form the desired shape, ensuring strength and uniformity. After shaping, the cookware undergoes an intensive polishing process to remove any imperfections and achieve a high-gloss finish. Stainless steel handles and lids are carefully welded onto the copper body for durability. Each piece undergoes strict quality control to ensure superior heat distribution and overall functionality. The pipe notching process in the Yaskawa Robots on Board welding system begins with the Motoman MA1440 arc welding robot positioning the torch with high precision. The robot performs high-speed arc cuts along the marked zones of the pipe, ensuring clean notches for later welding. A two-station positioner RWV2 rotates and tilts the pipe, allowing the robot to access multiple angles without manual adjustment. This setup ensures consistent quality and reduces cycle time. The MA-1440 robot features a 6-kilogram payload and 1,440 millimeters reach, making it ideal for confined welding tasks. The system's modular design enhances efficiency and reliability for industrial applications. The punching process on the Heiko Q3 CNC turret punching machine begins with the loading of a metal sheet, typically up to 6.35 millimeters thick, onto large, fully brushed support tables. These tables help stabilize the sheet, while repositioning cylinders allow easy handling of sheet dimensions, up to 2,000 by 1,500 millimeters. The machine uses 3 hydraulic clamps to fix the sheet securely during punching. The 6-axis CNC control system, TPC69 graphics, guides the entire operation. This user-friendly interface allows fast programming and real-time visualization of toolpaths. Operators input the desired punching pattern, and the system optimizes tool movements accordingly. The high-speed servo-controlled hydraulic punching head, capable of delivering 22 or 30 tons of force, drives the punch strokes. As the punching head moves into position, the sheet is automatically adjusted beneath it using X and Y axes movement, guided by the precise CNC control. Each tool is housed in a rotating turret, which supports either 12 or 20 tool stations depending on configuration. Fast turret setup and automatic tool indexing enable seamless switching between tool sizes during operation. One of the key features of the Q3 is its ability to rotate all tools, thanks to the integrated rotation axis. This allows punching at various angles without needing to reposition the sheet manually. Each turret station can accept any tool size, and fusion tools can also be used for specific complex shapes. The removable punch system and quick tool alignment setup ensure reduced downtime during tool changes. When punching starts, the stroke is executed with precise vertical motion, creating holes or shapes as defined by the program. A slug suction device underneath the working area removes waste materials, while punched parts may fall into a designated chute 300 by 470 millimeters. Throughout the process, vibration dampers reduce mechanical noise and impact, ensuring stable performance. The entire system operates with built-in CE optical safety lights and automatic oil spraying to ensure both safety and durability. This highly automated process allows the Heiko Q3 to produce consistent, high-quality perforations efficiently, making it ideal for modern sheet metal fabrication tasks. The P2 panel bender begins by precisely centering the sheet metal against mechanical stops. Universal Tool's upper blade, lower blade, counter blade, and blank holder automatically adjust to the geometry without retooling. Bending is executed through interpolated, servo-controlled movements of the blades. The direct drive system ensures high precision, while integrated sensors and Mach 3.0 calculate force in real time, compensating for material thickness 0.4 to 3.2 millimeters, deflection, and temperature. The P2 performs sequential bends on all sides with consistent accuracy. Optional P-tools enable tubular or tight radius bends, while CLA blades support segmented tabs. Each cycle guarantees repeatability and tight dimensional control across varied profiles. The HSTM-150S2 performs high-speed 5-axis milling of turbine blades with horizontal clamping for optimal chip removal. The process begins with precise positioning of the workpiece on the A-axis rotary table. A high-speed motor spindle, delivering both strong torque and high rotational speed, engages in roughing to remove the bulk material from the forged blank. Hydrostatic A- and C-axes ensure vibration-free movement, enhancing surface finish. The blade's complex geometry is formed by simultaneous multi-axis movements, with the milling head pivoting dynamically. Fine finishing follows, using HSC, high-speed cutting strategies to achieve tight tolerances and excellent surface quality, exceeding aviation standards. The machine's thermostable axes and rigid structure maintain precision under thermal load. Automatic tool changing improves efficiency during multi-step operations. The inclined axis arrangement ensures effective chip evacuation, and the modular, compact design allows easy integration into production lines. The result is a precisely milled blade with superior aerodynamic and mechanical performance. The assembly of the JU 55000 involves mounting the fixed and movable platens onto the machine bed, followed by installation of the short-stroke clamping cylinders for rapid mold force setup. The parallel lock nut system is then assembled for fast, precise locking. The movable platen support and guide mechanisms are installed to ensure stability during heavy mold loading. Finally, the injection unit with linear guides is mounted, completing the energy-efficient, compact two-platen system. The assembly of IDRA's third gigapress began with the foundation setup, where heavy-duty cranes positioned the massive base frame. The next step involved attaching the clamping unit, followed by the assembly of the die-casting components 8,000 to 9,000 tons, including the high-pressure injection system. Hydraulic and cooling systems were installed, with careful calibration of the temperature and pressure controls. The electrical system, including the central controller for automation, was integrated, ensuring seamless communication with peripheral equipment. After completing mechanical and electrical installations, initial tests were conducted to verify the operation. At Rimgem Steel, stainless steel production starts by melting scrap metal in electric arc furnaces, transforming waste into high-quality steel. The molten metal undergoes refining and alloying to achieve the desired chemical composition. It is then cast into billets and hot-rolled in advanced mills into long and flat products. Rebars are produced with diameters from 8 to 32 millimeters, featuring a pickled surface finish. Products are cooled, straightened, and cut to length. Strict quality checks are conducted at every stage to ensure world-class performance and corrosion resistance. Copper tube production starts with melting recycled and raw copper in a gas furnace above 1083 degrees Celsius. The molten copper is cast into billets, each around 450 kilograms, then cooled and inspected. These billets are reheated to 850 degrees Celsius and extruded through a 3,150-ton hydraulic press, transforming solid copper into hollow tubes. After hot forming, tubes are cooled to prevent oxidation. The next steps are entirely cold processes. Tubes undergo conical die rolling to reduce diameter and thickness, extending lengths beyond 120 meters. Further drawing through dies and floating mandrels refines dimensions at high speeds up to 1,000 meters per minute, producing tubes up to 1,200 meters long. Tubes are then straightened, cut to size or coiled, and annealed at 415 degrees Celsius to regain flexibility. After cooling, they are wrapped and packaged. The entire process ensures high purity, mechanical performance, and dimensional accuracy in compliance with EN 1057, suitable for plumbing, heating, and gas systems. Firstly, the process begins with raw material preparation. High-quality materials such as aluminum alloys or cast iron are carefully selected for their strength, heat resistance, and machinability. This selection is crucial as it guarantees the cylinder head's ability to withstand the stresses it will face in operation. Next, once the materials are prepared, the cylinder head undergoes casting or forging. In this step, molten metal is poured into molds or shaped under pressure to form the cylinder head's basic structure. The precision of this process is critical to ensuring the material achieves the desired shape and strength, laying the foundation for the next stages of production. Subsequently, after the casting, forging, the cylinder head moves to the machining stage. Here, advanced CNC machines are used to carve out precise features, such as the combustion chambers, valve seats, and ports. This step is key to ensuring the cylinder head matches the engine specifications, allowing for proper performance and efficiency once assembled. Following this, the next step involves component installation. After machining, essential components like gaskets, valves, springs, and seals are carefully installed into the cylinder head. This installation requires precision to ensure proper sealing and functionality when the cylinder head is integrated into the engine block. Each component must be placed with great care to avoid any defects that could impair engine performance. Then, the cylinder head undergoes rigorous inspection. At this stage, it is subjected to a series of quality checks to ensure it meets all necessary standards. This includes dimensional accuracy tests, surface finish assessments, and pressure and leak tests. Any cylinder head that fails these tests is sent back for correction, ensuring only the highest quality products proceed to the next stage. In addition, after passing the quality checks, the cylinder head may undergo surface treatment. This optional step includes processes such as milling, grinding, and polishing, which smooth the surfaces and improve their durability and sealing capabilities. The treatment also enhances the appearance of the cylinder head, ensuring it is both functional and visually appealing. Afterwards, once the cylinder head is treated, it moves to the final assembly stage. During this step, valves, springs, and seals are installed with great care. This is the final opportunity to ensure that all components are properly aligned and fitted before the cylinder head is integrated with the engine. The assembly process is essential to guarantee that the cylinder head performs optimally once in use. Finally, the completed cylinder head is carefully packaged for shipping. To ensure that it arrives at its destination in perfect condition, it is securely packaged to prevent damage during transit. The cylinder head is then ready for shipment, whether for use in high-performance vehicles or heavy-duty industrial engines. Production starts with U10 to 40 mm free-cutting brass rods, cut and CNC turned to achieve precise shapes. Milling, drilling, and threading operations follow to form detailed features. Components are then ground to maintain dimensional accuracy and a fine surface finish. After deburring, parts may undergo assembly and functional testing. Every step adheres to customer-provided technical drawings, ensuring the final products meet strict tolerance and quality requirements for industrial and electromechanical applications. The Hakko Kingsland CNC tube punching machine performs fast, accurate punching of any shaped holes in tubes of various shapes. Using the 60P hydraulic press with a 625mm deep throat and CNC control, it punches tubes up to 150mm in diameter and 3.6 meters long. Tubes under 80mm diameter can be punched through in a single operation, top and bottom. Molten aluminum is prepared in induction furnaces and purified using argon. The clean metal is transferred to machine furnaces and injected into molds by robots. After solidification, castings are removed, examined radiographically, and cleaned via tumble finishing or shot blasting. Precision machining follows on CNC centers and lathes. Final parts undergo dimensional, structural, and chemical tests. Only after confirming quality, the finished aluminum components are packed and shipped to customers. Billman's Foundry is a family-run workshop in central Victoria, Australia, known for its hands-on, custom casting process. For over 35 years, the Foundry has tackled unique, often complex jobs that other foundries won't take. Using traditional molding techniques and modern tools like electric induction furnaces and 3D printing, Billman's casts everything from bronze sculptures to large industrial parts. Each job is approached with care, skill, and pride in lasting quality. Foundry technicians select molds and pour 863 manganese bronze into rotating molds for even distribution. After cooling, castings up to 25,000 pounds are removed, cleaned, and rough-turned on vertical turret lathes. Bushings are cut, precision machined, deburred, inspected to prints, and packaged. Machining diameter reaches 160 inches. Lumina's die casting process uses fully automated cells, where shot parameters are controlled and recorded throughout production. 3 alloy types are melted in separate shaft furnaces to prevent alloy mix. The molten metal is degassed with automated flux injection, and quality is ensured through tests like density index and K-mold. After casting, parts undergo machining in CNC centers for complex tasks. Final products are washed, packed in an ISO 8 clean room, and undergo finishing processes such as shot blasting and heat treatment. Steel wires from 1-ton payoffs are straightened and fed into the loop unit, which arranges longitudinal and cross wires. At the welding section, intersecting points are pneumatically welded at 80 to 100 times per minute for wire diameters of 3 to 8 millimeters. Finished mesh is cut, stacked, and ready for dispatch. The automatic wire mesh welding machine welds cross and longitudinal wires to form mesh used in 3D panels and construction. Wires 2.5 to 6 millimeters are fed automatically, positioned, and welded at up to 120 times per minute using 42 welding heads. Mesh spacing ranges from 12.7 millimeters to 300 millimeters, and the maximum mesh width reaches 3.2 meters. Controlled by a PLC system with a touchscreen, the process ensures consistent and precise welding for structural applications. The perforated metal sheet is cut and shaped, then inspected to ensure hole precision. Surface treatment includes grinding, polishing, followed by leveling, using multi-roll straighteners to relieve stress and correct deformations caused by the perforation process. The process begins with radiation-tested raw copper and zinc. melted and continuously cast into billets using PLC-controlled horizontal casting lines. Billets are analyzed using an OES spectrometer, followed by macro and microstructural inspection. Approved billets are preheated and extruded through dies to form rods, bars, hollow sections, or custom profiles. Round rods range from E6mm to E110mm. Hex and square bars are also produced. Hollow rods eliminate the need for internal boring, improving material efficiency. Ingots, 73mm square, are mold cast for remelting applications. All products are precision cut, composition certified, and packed per customer requirements for global industrial use. The 3D sand printing process for engine blocks starts with creating a 3D digital model of the engine block using CAD software. This model is sliced into thin layers, which guide the printing process. Using a binder jetting technique, the printer selectively applies a liquid binder to the sand bed, layer by layer. The binder solidifies the sand, creating a precise mold. After printing, the part is carefully removed from the machine. The mold is then cleaned to remove excess sand and ensure smoothness. Once the mold is ready, the worker carefully dismantles it by breaking away the surrounding sand, ensuring the engine block shape remains intact. The process produces highly accurate molds for casting engine blocks. The X1 S-Max printer can handle parts up to 1000 by 600 by 500 millimeters in size. The carburetor adapter is produced through a combination of sand casting and CNC machining processes. The first step involves creating a wooden pattern that replicates the final shape of the adapter. This pattern is used to form a sand mold by packing Foundry sand around it in two separate halves known as the cope and drag. Once the sand is compacted, the pattern is removed, leaving behind a hollow cavity. Channels for pouring and venting the molten metal are added, and then molten aluminum is poured into the mold. After cooling, the solidified casting is removed, and excess material from the gating system is trimmed off. The rough casting is then machined to precise dimensions. A CNC milling machine equipped with a digital readout, DRO, and a rotary table is used for accurate alignment and positioning. The top and bottom surfaces of the adapter are milled flat. Mounting holes are drilled, and the central bore is machined to the exact diameter required for airflow. The rotary table allows for evenly spaced hole placement around the flange. The CNC mill operates at speeds up to 2000 RPM, allowing for smooth finishes and precise tolerances. After all machining steps are completed, the adapter is deburred to remove sharp edges and polished for a clean surface finish. The completed carb adapter ensures a secure and accurate connection between the carburetor and the intake manifold, improving both fitment and airflow efficiency in the engine system. In the shell molding process, a heated metal pattern is coated with resin-coated silica sand, which bonds to form a thin shell after a few seconds. The upper furnace cures the rear surface, creating a rigid biscuit mold half. Two such halves are glued together, enclosing a pre-formed sand core that shapes the hollow inside. The assembled shell is placed on a dry sand bed, ready for pouring. bronze is melted to 1,300 degrees Celsius and poured into the mold.
And when you see it flowing through the back like that, it means it's got his slags going properly. You get a constant flow of the slag dribbling through.
After solidification, the fragile shell and core degraded by heat are easily broken away. The result is a one-piece, weld-free bronze object with smooth surfaces and high dimensional accuracy. Brass billets are preheated and extruded through shaped dies to form solid or hollow profiles. These extrusions are then quenched, straightened, and cut to required lengths. Final products undergo spectrometer testing to verify alloy composition before machining or shipment. The aluminum shell casting process at Tironi begins with the preparation of a mold from a 3D design. The mold, made of steel, is produced by partner companies using advanced techniques. Before casting, a simulation is performed to monitor the aluminum filling and solidification process, ensuring the mold is correctly filled and identifying potential problem areas. Once the mold is ready, aluminum alloy is poured into the cavity through a gravity casting method, ensuring a precise and uniform cast. After the metal solidifies, the casting is removed, followed by deburring and sandblasting to remove excess material and achieve a clean surface. The aluminum castings undergo final quality checks in the laboratory. Thermic treatments, such as solution heat treatment, are applied to improve the mechanical properties of the cast. The process ensures high-quality aluminum components suitable for various applications. The melting process is carried out in 3 electric furnaces, each with a 28-ton capacity and 3,300 kilowatts power. These furnaces melt spheroidal graphite iron, GJS, austempered ductile iron, ADI, and isothermal ductile iron, IDI, using a mix of cast iron scrap, ingots, and ferroalloys, all stored and managed in-house. The entire melting process is controlled using ITCAC software, which conducts real-time thermal analysis to determine the chemical composition of the base iron. During pouring, the molten metal is transferred to a 4-ton pressurized ladle from the Progelta system. Inoculation occurs in this stage to prevent shrinkage defects and enhance the mechanical properties of the casting. The Itaka Stream system, supported by vision cameras, ensures accurate, real-time inoculant dosing for each flask, thereby optimizing spheroid formation in the ductile iron. Following casting, the flasks are stored in a controlled environment to allow gradual cooling and solidification. This step is critical to achieving the desired microstructure and preventing dendritic formations and segregations. After solidification, the shakeout process removes the castings from the molds. Finally, castings undergo a series of quality control tests, including temperature checks, nodularity assessments, chemical composition analysis, and further thermal evaluations to ensure all technical specifications are met before machining or delivery. At Carpinteria Mechanica, fabrication and machining processes are carried out across multiple specialized workshops. The welded metal workshop, Reparto Carpinteria, handles cutting, bending, and welding of metal structures. In the milling shop, Reparto Fresatura, precision milling is performed on components, while the milling and boring shop, Reparto Fresatura y Foratura, focuses on detailed milling and boring operations. The painting shop, reparto verniciatura, applied surface treatments such as sandblasting and painting. The MF20 production line forms multi-layer composite pipes through sequential processes of plastic extrusion, metal roll forming, and precision laser welding. Inner and outer plastic layers are extruded with thickness control, followed by metal tape forming using stress-minimizing roll formers. The formed metal layer is then laser welded using orbital seam tracking. Inline quality control ensures weld integrity. The line handles diameters from 10 to 40 millimeters and operates at speeds up to 80 meters per minute. The brass forging process begins with in-house design dies, used to forge components ranging from 20 grams to 12 kilograms. Core hollow forging is applied to reduce material usage. Forgings are checked through in-process inspections to prevent defects. After approval, machining is carried out using CNC machines to achieve the desired shape and precision. Various machining operations include turning, drilling, boring, reaming, milling, threading, and broaching. The company handles parts from 3 millimeters to 300 millimeters in size, maintaining tight tolerances down to 0.010 millimeters in turning. The Nargisa MC400 section bending machine, equipped with a special spiral die, is used to form 10 mm solid round bars into precise spiral shapes. It features 3 traction rollers, 2 lower adjustable rollers, and 1 fixed upper roller with 130 mm diameter and 40 mm hardened steel shafts. The rollers rotate at 7 RPM, enabling consistent. The machine straightens and feeds 3 to 8 mm wires automatically. Cross wires are dropped, positioned, and welded to longitudinal wires using SMC air cylinders. Mesh pulling and feeding are precisely controlled by Panasonic servo motors. It produces mesh up to 12 meters long and 3,000 millimeters wide at speeds of 80 to 100 welds per minute. Formwork panels are sorted, coated with a release agent, and assembled starting from interior corners using spacers, pins, and wedges. Exterior panels are secured, and wall brackets are installed every 60 centimeters with alignment ladders. Wall slab unions use knife ledgers fixed with brackets to prevent movement. Shoring forms and props support slab panels. Slab units are joined by stable pins. Braces and cabin liners ensure stability and safety. Final checks ensure correct leveling before concrete pouring. The robotic welding process begins with loading large components like booms, frames, and crane arms onto Robital SH and SHX Series 2-axis skyhook positioners, which handle up to 5 tons. The parts are precisely rotated and positioned for optimal welding access. A Robital PR3 axis gantry robot, along with a Yaskawa welding robot, performs the welding using 2 Fronius CMT twin advanced systems. Full axis synchronization ensures smooth coordination between robots and positioners. Advanced features like multi-layer welding, arc sense for seam tracking, and high-speed touch sensing enable accurate, consistent, and efficient welding of heavy construction equipment components. The 5-axis automatic adjustment system on the Okuma Multis U4000 operates through a 0.001 degree B-axis head that enables precise multi-angle positioning. The H1 dual-function spindle, capable of 12,000 revolutions per minute, adjusts its orientation via the B-axis to perform milling and turning tasks in a single setup. The Y-axis column feed allows for dynamic vertical movement during complex contouring or deep drilling. Coordinated with full C-axis spindles and an optional lower turret, the system executes high-precision machining with minimal repositioning. The process begins by mounting a 2 mm thick aluminum disc onto a lathe mandrel. Using the conventional metal spinning method, the operator forms the disc over the mandrel with scissor tools, applying sweeping motions to gradually shape the base of an electrical hub. The wall thickness remains constant throughout. The operator uses body weight and leverage to reduce effort, ensuring precise dimensions. Multiple forming passes smooth the surface. Once forming is complete, the component is deburred to remove sharp edges. After final quality checks and possible fabrication, the part is ready for use. Raw materials are welded and fabricated into blanks, then precisely machined on our Schiess VTL with a 200-ton rotary table. The gear teeth are rough cut using our 8-head gasher/hobber, then finished to AGMA standards on the MAAG grinder before painting and shipping. Mold specifications are discussed with the customer. Casting simulation ensures optimal filling. A steel mold is made from 3D design. Aluminum alloy is cast into a sand mold. Gravity die casting follows. Castings undergo lab tests, finishing, heat treatment up to 540 degrees Celsius, machining, and painting. Parts are pre-cleaned, racked, and submerged in an electrolyte bath containing sulfuric and phosphoric acids. A controlled DC current, typically 10 to 30 volts, is applied. Variables such as electrolyte temperature, specific gravity, cathode setup, and tank agitation influence results. Final rinsing, drying, and inspection follow. The process of creating cast iron objects at Fondazione Neri begins with the creation of a handmade model, crafted by skilled artisans. The model is divided into 2 parts, and after it is treated with a releasing varnish to prevent sticking, it is placed inside a large steel bracket. This bracket is then filled with special sand, which is carefully pressed around the model to form a solid mold. To ensure easy identification, the operator prints the customer's name on the sand, and it takes about 10 minutes for the sand to harden. Once the sand has fully set, the model is carefully removed from the mold, leaving a negative imprint of the object. This negative form is used to create the mold for casting. Molten iron, prepared in a 10-ton oxy-combustion melting furnace, is poured into the mold. The mold is left to cool, allowing the molten iron to solidify into the desired shape. Once cooled, the mold is broken and the cast iron piece is extracted. The piece then undergoes a series of cleaning and finishing processes to remove any imperfections and ensure a smooth, high-quality surface. These steps result in a finished product that is ready for installation, maintaining both durability and aesthetic quality. The production process of expanded metal begins by feeding a coil of sheet metal such as steel or stainless steel into a specialized machine. The sheet passes through a set of precision cutting blades that make a series of small, staggered slits across the material. Without removing any metal, the machine then stretches the slit sheet, expanding it into a continuous diamond-shaped mesh. This cut and stretch operation occurs simultaneously and continuously, allowing the mesh to form in a single step. The process ensures that the metal retains its structural integrity while increasing its surface area and strength. The resulting expanded metal mesh is then either rolled into coils or cut into flat sheets of specified dimensions, depending on the intended application. This method produces a lightweight, rigid, and non-raveling mesh suitable for various industrial and architectural uses. The Northwest HT 2500 hexagonal wire mesh machine weaves galvanized coated wire into uniform hexagonal patterns. Wire is continuously fed, twisted 6 times per cell, and interlaced into mesh of 15 to 80 millimeters openings. Operating at up to 160 meters per hour, it delivers consistent 3,300 millimeters wide mesh sheets. At the Royal Canadian Mint, the coin production process begins with engraving. Initially, a design is carved into wax plaster, then transformed into a metal matrix using a reducing machine. The matrix is polished and heat-treated before creating a punch to strike coins. In die production, lasers are employed to frost specific areas, like the Queen's portrait, reducing the time required for finishing. Afterward, blanks are cut from rolled gold and silver, polished, and prepared for final pressing in clean rooms to ensure the highest quality. Coins are then packaged and shipped to collectors. At Run Art Foundry, the bronze casting process begins with the dewaxing of shells in a ceramic kiln. Silicon bronze is melted in a carbon crucible and poured into the shells, which are supported by sand in a casting box. 3 people work together, ensuring a clean pour and removing impurities. Technicians prepare metal and ladles before pouring. A sample is analyzed to verify metallurgical quality. During centrifugal casting, rollers spin at high speed, pushing impurities inward for later removal. After rough casting is cut to size, parts undergo high-temperature heat treatment with quenching for hardness. A CNC lathe machines both diameters simultaneously to ensure concentricity. Turning the web plate to size, the ring is preheated and welded. After stress relieving in the oven, split lines and bolt holes are milled on a Schiess VTL. Teeth are gashed on an 8-meter Hoffler Haber, then ground on a 6-meter Hoffler CNC grinder. At Run Art Foundry, bronze casting involves melting silicon bronze in a carbon crucible, pouring it into preheated shells, and filtering out wax through the lost wax process. The bronze casting process involves melting brass and bronze in an inductotherm induction furnace. The melting crucible is lifted by crane, and the molten metal is poured directly into molds after cleaning, additives, and degassing as needed. The pre-annealed metal bar is inserted into a custom fixture with a 1.5-inch mandrel. The SSB3 scroll machine, using SPS control and a frequency inverter, bends the bar along a programmed path. Final radius adjustments are made with a 24-ton hydraulic press. The machine handles flat steel up to 60 times 12 millimeters. The MH900 heavy payload robot performs machine tending, material handling, and part transfer tasks with a 900-kilogram payload. Using its 4,683 millimeters horizontal and 6,209 millimeters vertical reach, it efficiently moves large components like car bodies or pallets. The DX200 controller ensures precise motion and safe operation. Scrap metal is shredded by a vertical hammer shredder into smaller pieces. The material then undergoes downstream milling and separation. Eddy current and density separators extract brass from other metals. Further processes purify the recovered brass. This method efficiently isolates brass from mixed scrap, enhancing its purity and preparing it for resale or reuse. Metal sheets are simultaneously cut and stretched to form expanded mesh with diverse patterns, then flattened, framed, welded, and surface treated through lacquering, galvanizing, anodizing, electropolishing. The bell, weighing 15.684 kilograms, 34,577 pounds, is rung by a machine with a clapper weighing 498 kilograms, 1,097 pounds, and a yoke weighing 1681 kilogram. The machine operates with a diameter of 287 centimeters, and the largest thickness is 22.3 centimeters. The Izumi 800T die casting machine produces aluminum radiator parts with a shot speed of 5 meters per second or higher. The process involves ladling, mold opening, product extraction, spraying, and inserting. The machine molds 2 blades in a 30-second cycle using a gravity mold. Molten aluminum at over 660 degrees Celsius is filtered to remove impurities, then cast into ingots using semi-continuous molds. Once solidified, ingots are removed from molds using hydraulic, ensuring smooth extraction without damage to the ingot. The casting machine operates at up to 8 tons per hour.